All right, we're going to talk through these 4.2, 4.4 AP problems. So in this one, we got 78 students, 35 are in the band, 32 on our sports team, so that's 67. But then there's 16 who are not. If you add all those up, you get 83. And that just, if there's 78 students, there's 83 like things happening. So that means there has to be some overlap there. So if I do 83, like it's not really people, but 35 band entries, 32 sports entries, 62 non-entries. There's like 83 entries for only 78 people. That means 5 people must be entered in 2 slots. So band and sports is the one we're going for there. But mutually exclusive means they cannot happen together. If one is happening, the other cannot. And these are not mutually exclusive because we just kind of talked through the fact that there are 5 people that are in band and sports team. Okay, number 2, which of the following correctly interprets mutually exclusive? So mutually exclusive means the 2 things cannot be true at the same time. So if I look through these options, A is the right answer, but I was kind of hoping it would be E, so I could talk through a couple wrong ones. But let's look at B, rooting for the home team and purchasing food during a game. I mean, just in general, can you root for the home team and purchase food during the game? Yeah. Home team, purchase food, boom, there are 120 people. And all of these B, C, D, and E are going to do one thing from these over here and one thing from these over here. But A, rooting for the home team and rooting for the away team, that you can't do that. So we had 180 people rooting for the home team, 70 people rooting for the away. There is no overlap. There's no duplicates. So that is mutually exclusive. Number 3, probability we get one that's not a size small. Well, there's 50 shirts. 10 of them are small. 40 of them must be not small. There's 50 total. 40 out of 50 is 0.8. Number 4. So you got to remember on this one, there's like 2 ways it could happen. I could have made a tree, and we'll probably do a tree or something in class, so you can see what I mean by that. But I'm sure they're in the video notes too. But this could be Adam then Ella or Ella then Adam. So there's 5 ways Adam, the first person picked, could exist, and one of them is Adam. And then once Adam's gone, there's only 4 people left, so he's gone now. And then the probability of getting Ella is 1 out of 4. So it's 1 out of 20 that'll go Adam then Ella. Ella then Adam is the opposite. Same reasoning, but just opposite order. And then 1/20th plus 1/20th is 2/20ths or 1/10. Really surprised. Oh, they did put 1/20th as an answer. Yeah, 120 is probably a really common wrong answer. Okay, R, F, and S mutually exclusive. So I'm looking back. F represents the event that they selected the first discount. S represents that they chose the second discount. Well, you had to choose one of the 2. You can't choose both. So the probability that you chose both is 0, because that can't happen. This little upside down U means and. If you see the U, it means or. But this means the probability of the first event and the second event happening at the same time is 0. Number 6. So this is simulation is like, I don't really know how to do the math, but let me set up this situation that is a representation of the situation and see what happens. So what they're doing here is they're kind of doing an estimate or like a simulation to see how many people had to wait 0 minutes, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, whatever. Okay. So, oh no, 0 people had to wait more than 8 minutes, 18%. One of the next 10 callers had to wait 34% of the time. 2 of the next 10 callers had to wait 28.4% of the time. 3 of the next 10 had to wait. So at most, 2 of the next callers, I'm going to find the numbers for 0, 1, and 2. So that's here, here, and here, and just add those up. Number 7. So this is more like a tree. I'm just kind of starting to get into it. So here they're saying roll a die, roll another die, and then subtract. Okay, so I skipped a page there of my scanning things in. But the answer to that one is C. And the way I would think about it, if I look at my, I don't have the sheet of paper on there, I'm sorry, but if I look at the answers, there has to be negatives, because you can't just say like, oh, this one's going to be bigger all the time. So I know it's going to be C or D, just looking through my answers. And then the only way I'm going to get like -5 is if one die shows a 1 and the other shows a 6. And that's pretty rare. And if you look at D, it's kind of portraying that as though it's equally likely as anything else. But if you subtract the die, the most common thing you're going to get is 0, and then 1 to -1, slightly less. The dice will be close to each other, but it's just going to be more rare that they're far apart. So your answer is C. And I apologize for not having that page on there. Number 8. So this is a huge thing to understand about probability. It is, for many rules, long run frequency. So it's not saying like this will happen every single time we do 6 rolls, 10 rolls, 100 rolls, whatever. It's just over the long run. The law of large numbers says that eventually, if it's fair, less than 3 is 1 and 2. So 2 out of 6 is 1 out of 3. So over the long run, the law of large numbers says that we should get really close to 1 out of 3. It does not say that for 3 rolls, this will happen. For 2 rolls, this will happen. A coin doesn't know, or a die doesn't know, well, the last 2 times I rolled, I was a 4, so I better be something different this time. That's not how it works. It's completely unpredictable, completely random in the short term, but in the long term, we can tell what's going to happen. All right, my video is getting a little bit long here, so I'm trying to speed it up. So simulation is like, I don't know how to do the real math, but let's try to set up a situation of making at least 3 out of 5. So let's look at a random digit table. And how could we simulate this scenario? Well, the probability he makes the basket is 80%. So what I want is 80% of the numbers I choose to represent make and 20% of them to represent miss. So if you look at E, 0 through 7, that's actually 8 numbers. So I'm going to roll a die. If I roll a 0, or not roll a die, but look at a random digit table, and if I see a 0 through 7, they made the free throw. If I see an 8 or 9, they missed the free throw. Then I'll repeat that over and over again. Part B is not awful. It's just backwards because it's like 2 options, so 20% to make, and the other ones don't make sense. Number 10. So if they purchase a lawnmower, the probability they purchase, a customer who purchases a lawnmower will also purchase an extended warranty is 0.68. Well, you can't purchase the extended warranty unless you bought the lawnmower. So that's just saying, once I know they bought the lawnmower, 68% of them will buy the warranty, but that's the same thing as saying for all customers who purchase a lawnmower, 68% will. Yeah, so that's just kind of rearranging the verbiage there. Again, these two are not true. I have no idea what's going to happen in the next 25. It's not like at the 24th customer, some magical math fairy comes down and says, oh, only 16 have purchased an extended warranty. So in the 25th one, we have to make sure the math lines up. That's not how it works. We don't know anything about what's going to happen in the short term. And 25 is very short term. 100 is short term. 1,000 is short term. I just know over the long, long, long run, probability will get us there. Number 11. So this is kind of the long run thing I was saying. Probability that you'll be asked to interpret or participate in an online survey is 0.4, 40%. But again, that's long run. Over like millions and millions, approximately 40% will be asked. So she's saying for the next 5 visitors, 2 will be asked to participate. Well, again, that's thinking that there's some magical math fairy, that after 4 visitors, if things aren't right, the magical math fairy is going to step in and make sure that things are okay by 5. And that doesn't make sense. So 40% or 0.4 represents probability in the long run over many visits. It does not mean in the next 5 I'm going to get exactly 2. Think of flipping a coin. It's 50-50, right? Does it mean if I flip it twice I'm going to get 1 heads and 1 tails? Like the coin will know it was heads and it knows it has to fix things and it'll be tails on the next one? That's not how it works. Number 12, which of the following cannot be the probability that the selected car will be green? Well, if I add up these 3, that's 100 cars. There's only 100 cards left, so even if they were all green, the highest it could be is 100 out of 200 or 0.5. And I kind of snipped my answer, but answer E is down there. It says 0.6, so that's the answer. And then number 13, I've been referring to this a couple times. The law of large numbers says that as the sample size increases, The mean gets closer and closer to the true population mean or the theoretical mean. So when we're working with die or dice or coin, something we know what the theoretical probability is, 1/6, 1/2, whatever. As the sample size increases, we should get closer and closer to that. It's not like a direct line. It's not like it just gets closer, closer, closer. But over the long run, let me see if I can. Yeah, I don't know. I can't think of a great example there. But over the long, it might be. Oh, that's the word I was looking for. Oscillating. So you might get something like this where your probabilities kind of wiggle back and forth. Like say this line is 0.5 and you're flipping tails. After you've flipped, oh, you can't see that. Let's say this line right here is 0.5 and you're flipping coins. After like 2, it might be that 70% are heads. And then down here, it might be that only 30% are heads. And then now it's 60% are heads, 40% are heads, 55, 45. But over the long run, you'll end up on that 50% line. In this example, that's just a supporting example. All right, all set.